Grover is one of the most famous algorithms in the quantum computing field. We also refer to it as Grover search algorithm, because it's actually useful to search for some correct solution in a list of many possibilities. In Grover, it's important to highlight this aspect. We are supposing we know the correct answer to a question, but we still need to search for it into a list of answers. This can be useful, for example, to find the key which unlocks a door among n different keys. Okay, so you need to search for the specific key. Classically, in the worst case scenario, you will need to test all the keys before finding the correct one. It means that the classical algorithms which solve this problem have a worst case complexity of the order of n, where n is the number of the keys. Grover instead leads to the correct answer with a probability close to 1, with a number of algorithmic execution proportional to the square root of n. Pay attention, I said probability close to 1, not exactly 1. In fact, Grover is not deterministic. Anyway, we gain a quadratic speedup. To make the lecture more fun, let's make a practical example. Suppose you are partying with many of your friends. Perfect. You are enjoying your coffee while listening to music, and at some point you get distracted and someone, without you notice, pours some sugar into your coffee. This is a disaster, because you like to drink the coffee bitter. Now, you absolutely need to find who is responsible of this. Luckily, the guilty friend left a hair inside the coffee mug. This is perfect, because you have a DNA machine in the dressing room. So now you only need to compare all the DNAs of your friends with the one of the hair, and yeah, then you will find the guilty person. Well, classically, this procedure in the worst case scenario will require a number of DNA tests equal to the number of friends. But you are even luckier, because you know quantum computing. As you will see, using the DNA machine as a quantum oracle, we are going to detect the guilty friend with a less number of tests. Let me now go over the main steps of the Grover algorithm with the help of a circuit diagram. For more mathematical details, I suggest you to watch the dedicated lecture you can find in the course Introduction to Quantum Computing. So, we consider a quantum circuit composed of n plus 1 qubits. The first n qubits compose the input register, while the last qubit is the ancilla. The first step. As usual, with the quantum computing algorithms, we start preparing the state. We leave the input register into the computational 0 state, while we apply a NOT gate to the ancilla, so that it stays into the computational 1 state. This will be useful later to enable the phase kickback effect over the input register. Second step, we apply Hadamard's to all the qubits, preparing the maximally superposed state. Then, at this point, we apply the oracle operation. The task of the oracle is to mark the target state by flipping its amplitude. The oracle in our example can be seen as the DNA machine, which is able to detect the guilty person in the room. Then we apply the so-called diffusion operator, which is defined as you see in the screen. The effect of the diffusion operator is to invert all the amplitudes of the system around the average amplitude. Acting together with the oracle, the final effect will be an increasing of the target amplitude and a decreasing of all the remaining amplitudes of the system. We are going to speak in more details about this kind of topic in a future lecture. Well, the game is done. You only need to repeat the sequence oracle diffusion operator a proper number of times, a specific number of times, as you will see. As in the case of the Doi-Jozsa, we are going to build our quantum circuit in a modular way. With this I mean that we will compose the quantum circuit by summing some layers. An initial layer in which we prepare the state, middle layer which contain the alternance of oracles and diffusion operators, and a final layer to add the measurements. Let's implement it with Qibo. Let me start by importing some packages. We are going to import random, which is a package that can be used to generate random numbers. Random. Then we import NumPy, that you already know. Import NumPy as NP. And then we import also matplotlib, which is a graphical package that we can use to make some plots. Import matplotlib.pyplot as plt. Then we can import Qibo, and we can also import from Qibo some modules and classes. So from Qibo, import circuit gates. Finally, let me import from scripts, which is the collection of functions already coded by us and useful for these lectures, some useful function from utils, and some plot scripts. From scripts, import utils and plot scripts. Fine. Now we are ready and we can set the backend. Qibo.set backend equal to QuiboJIT. Okay. Now we just want to prepare the notebook to the following part. Since we are going to exploit the quantum state of the system in order to encode some specific information, in particular we want to keep track of some specific state, the one corresponding to the guilty person in the room, then it will be useful to associate some numbers, thanks to which we can count the people inside the room, to some bit strings that are going to be associated to the components of the states. For doing this, we can use the generate bit string combination function that we already used in some past lecture. So we start by setting the number of dimensions, so the number of qubits. In particular, we set it to 5, for example. Then we can also set the number of shots, and this will be useful because we would like this time to try to see what happens if we simulate a realistic output of the quantum circuit. Let me set a high number of shots, for example 1 million. And then we can indeed generate the bit string list. So we can call bit strings equal to utils dot generate bit string combinations, and then we just need to provide the number of digits we want in the string. Perfect. We can also print the list. Print bit strings. As you can see, we have all the possible combinations of zeros and ones inside a string of length 5. Let me check now if the bit strings generated are corresponding to the possible number of quantum states that are 2 to the 5, 32. So we can print len bit strings equal to 2 to the 5. We should get true if actually we are building 32 possible bit strings. Indeed, we have true. And finally, we can, for example, pick up a random element from the list using the random package. So we can say test bit string equal to random.choice from bit strings, and we can print test bit string. For example, we get 0000. If you repeat this operation, you get a different bit string. For example, 11101. Fine. Now we have a list of bit strings that correspond to 32 numbers from 0 to 31 that will be our people inside the room in which we were partying. Now, since we are discussing about people, I would like to make it a bit more fun by associating also some names to these people. We can do it, for example, by using the faker package. This is a Python package, thanks to which we can generate fake names. So we are not referring to real people here. You can do that, or you also cannot do that. I mean, it's the same. It's just for the sake of having some name associated to the numbers. So we can import the faker library. If you don't have it, you can install it by typing pip install faker with the capital letter F. Fine. Now we can call it for 32 times, and we can generate a name each time. And so we append to this names list the names. As you can see, now we have a list of names, and one of them will be the guilty person in the room. Now, since we are using Grover, you should think that we already have the answer. The answer is in the air inside our mug. But still, we need to search for the name of the person. So we need to apply the DNA test. So let us just check which is the name associated to the guilty index that I set to be 11. You can change the number if you want. It's just an example, 11. So in this case, we have number 11, guilty Nicholas Harris, corresponding to the state 01011. Now the problem is set up, and we can go over the main steps of the Grover implementation. Okay, so since we are going to build our quantum circuit which applies the Grover algorithm in a sequential way, so applying some layers, let me implement the two layers which are at the beginning of the circuit and at the very end of the circuit. This is a similar approach to the one we used implementing the Deutsch-Jozsa circuit. So the first layer, the initial layer, will be the one in which we prepare the state into the 000 state for the input register and the 1 for the ancilla, and then we add the superposition. So what you can do, since the structure of the function is similar to the one you already saw in the previous lecture, is we have a build initial layer function, we pass the number of qubits, and then we return a circuit. So you can type C equal to circuit, and then we need to set n plus 1 qubits, because we want the input register plus the ancilla. Then we add a NOT gate to the ancilla, since the qubits of the input register are by default initialized to be in the 0 state. So we say c.add gates.x applied to n, since the ancilla is the last qubit and we start from 0, the counting. So n means the n plus 1 qubit of the system. And finally, we need to add superposition. So we just type for q in range n plus 1, because we want to apply superposition to all the qubits of the system, c.add gates.hadamard applied to q. Once this is done, we have our quantum circuit. The final layer of the circuit will be a bit different from the one of the Deutsch-Jozsa algorithm, because here we just need the measurement gates. So we initialize a circuit, C equal to circuit of n plus 1 qubits. I'm calling the circuit C because I'm returning C. If you want to change the name of the variable, you are free to do whatever you want. And then we just add c.add gates.m star range n, because we are interested in measure just the input register. Now we have our build initial layer and build final layer functions. We can combine them together, and in order to see what happens if we execute just the initial and the final layer of Grover without adding in the middle any oracle or any diffusion operator. We can build a circuit C equal to build initial layer, and we pass n, plus build final layer, and we pass again n. We can draw also the circuit. Print c.draw. As you can see, we have the 5 qubit corresponding to the input register, initialized directly with the Hadamard gate, and then we have a NOT gate to get the state 1 for the ancilla, and then the Hadamard. Finally, we have the measurements on the input register. What happens if we plot the input register amplitudes after the execution of this circuit? You can call the function plot scripts dot plot input register amplitudes, and we need to pass, as you probably know from the previous lectures, the Qibo state. So we need to execute the circuit, open and close bracket, dot state. This will be compute the final state in terms of Qibo outcome object, and then you will access to the state object in Qibo, collection of the amplitudes in a few words. As you can see from here, the amplitudes are all the same. Indeed, we are in the superposed state. We can also have a look to the same effect, but looking directly to some more realistic output, which can be the probabilities. These probabilities are computed by collecting all the final states collapsed, so frequencies, zeros and ones, and then recombining them together into probabilities. And you can use again a function that we already implemented, so you call plot scripts dot plot Grover probabilities, and in order to use this function you just need to pass to the function the circuit, C, and the number of shots and shots. From this plot you can see some different behavior of the previous plot. So again you see clearly the superposition. Indeed, the probability of getting the states is practically very similar. The value is different, of course, because here you are seeing the probability, and since we are using the shots, we don't have exactly the same probability for each state. This is slightly different, but not a lot, because we set a very high number of shots. Okay, I think after this we can finally go on and see how to implement the Grover oracle. Well, now we need to implement the Grover oracle. Since we are encoding our problem inside the components of the quantum state, then we need a circuit which is able to manipulate the input register state by marking the guilty component in some way. Typically, we use the trick of flipping the sign of the amplitude we are searching for. If you want some remains of the mathematical description of this step, you can think to the oracle as an operator which implements the function you see here in the screen. This takes as input a bit string of length n and returns or 0 or 1. In particular, we want it returning 1 in the only case in which the input bit string x corresponds to the one representing the guilty person. In practice, as you can see from the screen, this will flip the sign of the amplitude only when x is the guilty bit string. Now, speaking more Qibo friendly, which can be a good way to implement such an operator? The solution is to use a multi-control gate. A multi-control gate is a gate which is controlled by many qubits. If we use all the input register to control a single gate applied on the ancilla, we know that this gate will produce an effect on the system only in the case in which all the qubits are simultaneously in the state 1. This will be done by only one component of the state, the 1, 1, 1, 1, 1, indeed. So, if your guilty state is the 1, 1, 1, 1, 1, well, the game is done. You set a multi-control gate using the input register as a controller, and then you will register a phase flip due to the phase kickback received from the ancilla. But what about a situation in which the guilty state is another one? Then you need to adjust the oracle so that the triggering component is different from the 1, 1, 1, 1, 1. For example, you can implement it by modifying the state, applying some NOT gates to the qubits which, in the bit string, correspond to a 0. On this way, you will leave the global state untouched, but the actual component which is activating the gate is the one corresponding to the guilty state. To give an example, if you want to activate the gate with the 0, 1, 1, 1, 1 state, then you need to apply a NOT gate to the first qubit of the input register. Then you apply the multi-control NOT, and finally you restore the original state by reapplying the NOT gate to the first qubit of the input register. Then now let's go to the code to see this effect in practical terms. Now we can have a look to the implementation of the oracle we just introduced. So what we have is a function which takes as argument the guilty index and the number of qubits. This is useful because from the guilty index we are going to compute the bit string, and then we are going to check in which position we get a 0 in order to reconstruct a state that actually is going to trigger the multi-control gate in the way we like. So we just take a guilty index and the number of qubits. The bit string, the correct bit string, is the one that corresponds to the guilty index into the bit strings list. Then we set up a circuit composed of n plus 1 qubits, input register plus ancilla. Then we set a list of zeros. This is an empty list in which we are just going to save the index corresponding to the position in which we get a 0. And then we do it for each 0 we face into the list. Indeed, we are here looping over the bit string. In each element, in each bit of the bit string, we check if it is a 0, then we append to the zeros the index. This is the index corresponding to the bit inside the bit string, thanks to the enumerate function of Python. Then we add an X gate to each qubit which appear in the list of indices in zeros. Then we apply a multi-controlled gate controlled by all the qubits of the system and apply it to the ancilla. And then we remove what we did before by reapplying the X gates. We can execute the cell, and then we can use it. We can use this function to create our circuit. Indeed, we can say C equal to build oracle. Then we need to pass the guilty index, and the number of qubits n. And then we can print the circuit. C.draw. As you can see, since our guilty index is 0, 1, 0, 1, 1, we saw it before corresponding to the number 11, then the oracle is implemented with a multi-controlled NOT gate. And before and after the multi-control gate, we have a couple of X gates that corresponds to the position 0 and 2 in the bit string. Indeed, the position in which we had a couple of zeros. Perfect. Now we can build the whole circuit involving the initial layer, the oracle, and the final layer, and we can have a look to what happens. So C now is going to be computed as build initial layer n plus build oracle of guilty index and then plus final layer build final layer of n. And we can draw the circuit. C.draw. As you can see, we have usual situation. We prepare the initial state to be in the 0001, adding a NOT gate to the ancilla, then we add another NOT gate to each qubit of the system, then we have the oracle, and finally we have the measurements. Perfect. Now we can execute it, and we can use the plot input register amplitudes method in order to visualize the final state after we execute the circuit. We can do that by typing plot scripts dot plot input register amplitudes, and then, as you know, we must provide to the function the Qibo state object. So we execute the circuit, and then we just type dot state open close brackets. From this, you can see the amplitude of the final state. What happens? Basically, we start from the maximally superposed state, and the effect of the oracle indeed is the one of flipping just one component, which is the component 0, 1, 0, 1, 1, the one that we wanted to mark as guilty. Now we can also have a look to the probabilities. So which are the probabilities associated to this set of amplitudes? We can call, for doing this, the function plot scripts dot plot Grover probabilities, and we just need to give to the function the quantum circuit C and the number of shots. Fine, what we get is basically something very similar to the previous plot of the probabilities. This is because of the definition of probabilities on top of the amplitudes. So basically the important point here is that even if the amplitude was flipped, then the magnitude was the same, and so what we get in the very end, practically, is the same probability. So we are still, in terms of probabilities, measuring the same configuration. Now is the moment to proceed with Grover and to build the diffusion operator. Okay, finally we need to implement the diffusion operator. In practice, we want a quantum circuit which is able to amplify the amplitude of the guilty state while reducing the amplitude of the others. We started from a superposed state, then we flipped the guilty component. So now we can exploit this new state as starting point to perform what can also be defined as inversion around the average amplitude. In a few words, after flipping the sign of the guilty component, we can apply the operator you can see in the screen, which actually performs an inversion of the amplitudes around the mean amplitude value of the system. This provokes a considerable increasing of the guilty amplitude, together with a decreasing of the amplitudes of the other states. In terms of implementation, we do this by applying a series of gates to the system. In particular, we apply an Hadamard gate and a NOT gate to each qubit of the input register. Then we apply a NOT gate to the ancilla, and this is needed to preserve the correct sign of the inversion operator. At this point, we apply a multi-control NOT gate to the ancilla, using all the qubits in the input register as control. Finally, we reapply the NOT gates and the Hadamard gates to the input register. The effect of all these steps provokes the inversion around the average amplitude value. So this architecture may seem quite obscure, if just mentioned as list of gates. For this reason, we prepared a separated lecture in which you can find more details and motivation about this gates choice. Well, this final implementation is a crucial part of the Grover algorithm, and it is very important to understand the joint action of the oracle and the diffusion operator. What you can do at this point is to repeat the sequence oracle diffusion operator until the probability of finding the guilty state after computing the measurements is very close to 1. It is important to mention that this configuration can be reached after a precise number of repetitions of the sequence oracle diffusion operator. In particular, we can maximize the probability of finding the guilty state executing this routine pi divided by 4 times square root of m times, where m is the number of items you need to explore as candidates to solve the problem. After exceeding this number of times, Grover will show some periodic behavior, which will lead to a worse result until a new optimal configuration is reached. The takeaway message is: repeat the Grover routine the optimal number of times. More is just a waste of time. Now, let's go to the code in order to implement the diffusion operator. Now is the moment of having a look to the code in which we actually implemented the diffusion operator. As you can see from this function here, that's already coded, what we have is a function which takes n as argument, as usual, the number of qubits in the input register. Then, going through the lines, we are initializing a quantum circuit of n plus 1 qubits, input register plus ancilla. Then we apply an X gate to the ancilla, and this is useful to preserve the sign of the diffusion operator, as already mentioned. Then we apply this Hadamard gate and NOT gate to each qubit of the input register. Then we apply a multi-controlled NOT gate to the ancilla, controlled by the qubits of the input register. And finally, what we can do is to reapply the NOT gate and the Hadamard gates to the input register. Finally, we return the circuit. So let me execute the circuit. Perfect. So let me now put all the pieces together into the build Grover function, in which basically we are going to put together the initial layer, the oracle plus diffusion operator, and finally the final layer. So what we can do is that first in this function here, which takes the number of qubits of the input register plus the number of times we want to repeat the Grover routine as arguments, okay, we can start by setting the circuit C equal to circuit and number of qubits equal to n plus 1. Once time more input register plus ancilla. Then we add to the circuit the initial layer, and we can act like the circuit is a sort of list. So we can say plus equal build initial layer, and we pass n as argument. Okay, now we have our initial layer, and what we should do is to add the oracle followed by the diffusion operator. So in this loop here, which loops over the number of steps we want to do, we say C plus equal build oracle, and then we need to provide to the function the guilty index and the number of qubits in the input register. Moreover, we can say C plus equal build diffusion operator, and we provide the function with the number n of qubits. Finally, what we can do is to add the final layer, so just the measurement gates. So C plus equal build final layer, and we pass n. This will conclude our quantum circuit. Now, we can build the circuit actually in practice, for example by setting the number of steps equal to 1, and then we draw it. So C equal to build Grover, we pass it n, and n steps equal to 1. And then we can draw it. So print C.draw. So as you can see here, we have quite more complex circuit in which we start preparing the state, an X gate to the ancilla, then the Hadamards, then we have the oracle, so a couple of X gates here and the multi-control gate. The Hadamard, these are not well aligned in the schema. From the output, you can see the whole set of gates we are applying to the qubit system. We prepare the state, then we apply the oracle, then we apply the diffusion operator, and finally we add the measurement gates. So now we can execute it and plot the Grover probabilities as we did before, and we see what is going to change. So we can say plot scripts dot plot Grover probabilities, and we need to pass to the function the circuit C and the number of shots. What we see is actually something very interesting. Indeed, we see the probability of getting all the states which are not our guilty state is decreasing. Instead, the probability of getting the target state, so the guilty state, is increasing. Indeed, our guilty state was 01011, if you remember. So what happens if we repeat Grover more than one times? So we build the circuit. We just need to pass as arguments the number of gates of the input register and the number of times we want to repeat the Grover, and then we can print the circuit. So print C.draw. As you can see, we have a similar structure of before, but now the pattern is repeated twice. Again, we can call the plot Grover probabilities function. So plot scripts dot plot Grover probabilities, we pass the circuit and the number of shots. Again, the amplitudes of the non-guilty states are decreasing, while the amplitude of the guilty state is increasing. Now, we want to understand how many times we want to do that. And also, since we want to get the right answer with a probability close to 1, it's important to see which is the probability that we are now getting corresponding to the guilty state. So in this cell here, we are just taking into account the final state we get if we execute the Grover circuit here. Then with these calculations, we are taking into account only the amplitudes of the input register. We are computing the probabilities associated to the amplitudes, and then we just print a sentence in which we highlight which is the guilty state and with which probability we are for now getting the correct answer. So let's execute it, and we see, okay, the guilty state is 01011 with probability 0.6 corresponding to Nicholas Harris. So the point is, the answer is the correct, but we are still far from an optimal configuration in which the probability of getting the guilty guy is close to 1. So from the theory, we know that the optimal number of Grover steps should be pi divided by 4 multiplied by the square root of m, where m is the total number of items of our set. Let's compute this value to see it. In the case of 5 qubits in the input register, we know that we should repeat the Grover pattern at least 4 times. So we have this 4.44. We should repeat it or 4 or 5 times, then we can decide. Okay, so now we can have a final check. So we can repeat the Grover experiment, but increasing the number of times we repeat the couple, oracle, and diffusion operator. For doing this, we can define an empty list, prob target, so target probability. We also define a number of times we want to repeat the Grover, a maximum number of times, so n equal to 10, for example. And what we should do now is to say, okay, for E in range n, what we do is to repeat the Grover. So we allocate a circuit, which is given by build Grover, in which we pass the number of qubits in the input register and the number of times we want to repeat the pattern, which is E, because it's growing. And then finally we call a function which is called utils dot compute max probability, and we should provide the function with the circuit and the number of shots. We append this value, it will return the probability of the guilty state to the probability target list. So prob target dot append, and we append the output of this function. Perfect, so now we can execute the cell, and after a while, yes, we get our list of probabilities. Now n is set to be 10, and so we repeated 10 times the experiment with an increasing number of repetitions. In this cell, the last one, you see a plotting function in which we are just plotting the probability of getting the guilty state as function of the number of times we repeat the sequence, oracle, and diffusion operator. Let's print it. Perfect. So what you see here is a sort of periodical behavior. We stopped the experiment to number 10, but you could go on, and you will see this pattern that over time is repeated. As you can see, the optimal number is represented by the red line, the red vertical line, and what you see is indeed that the maximum value is expected to be between 4 and 5 Grover repetitions. This is just a cross-check to show you that indeed if you go on with an increasing number of Grover repetitions, then you will get the correct answer with a probability that's decreasing. Finally, we can take this code here. We already computed. We know now that the optimal number of times we need to repeat the experiment is 4 or 5, so we can set 4, for example. So we build the Grover with 4 layers in the middle, and then we can print the final probabilities that will be closer to 1 for the guilty state. And indeed, you will see a probability of 0, 1, 0, 1, 1 to be very close to 1, and the other one to be very small. With this, we finish this lecture about the implementation of the Grover algorithm, and we move on with the last lecture, in which we are going to delve deeper inside the implementation of the diffusion operator and the oracle.